Hello AP Calc BC, this is Chapter 10, Topic 2, which is cycloids, two-dimensional vectors, and vector operation. Okay, so by the end of today, or this lesson, you should be able to understand the definition and application of cycloids for finding arc length. So in last section, we found arc length with integrals of, and used the derivatives of parametric functions. And now we're going to talk about using cycloids to do that. And then we're going to use two-dimensional vectors to find distance, speed, acceleration, and some other related quantities of moving objects. So the first thing that we want to talk about is what is a cycloid. So what a cycloid is, it's something that is moving along a path. And an example is a wheel. And if you think about it, as a wheel rolls, the overall motion of the wheel, if you're watching it from a distance, you just see this object moving along a straight line. But what a cycloid shows, or what a cycloid is it picks one point on that wheel and it traces that one point as it moves. So real quickly, I'll jump to the next slide. And so this line right here, or this curve rather, which is formed by picking one point on a wheel and tracing it as the wheel moves along a horizontal path, that's a cycloid. So the shape that this point on the wheel makes is a cycloid. Okay. So let's suppose that we have a wheel of radius A and it's rolling along this horizontal line without slipping. So it's got uniform motion. So the path that it traces on the wheel's edge is the cycloid that we just saw, and P is originally at the origin. So your point, what they're saying is that when we start this whole process out, your point is here, right? And so what we've done is we've traced the path of the point from the origin to here. Okay. And so then you can see as we move through the rotation, we have this shows our angles of pi and where the point is as we move through the rotation, right? So when we've made one rotation, when the wheel has made one full rotation, it looks like it makes almost a semicircle, maybe a little bit less than a semicircle. And so we've moved through 2 pi radians. And then if we do that whole thing again, where we've done 2 rotations, we've moved through 4 pi radians, and so we create another bump like that. So then this brings us to example 1, which is to find parametric equations for the path of the point P in this figure below. Okay. So let's start off by making a few statements. Okay. So let's suppose that the wheel rolls to the right with our point P being at the origin when let's see, because they have this at theta and t, we'll say when t is 0. Okay, so at the very beginning of our problem, if we roll the wheel backwards, point P is over here at the origin. So just one thing that we want to talk about, the angle that we're going to measure this wheel through, we'll measure it in radians, and usually we do that when we're working with cycloids like this. Now, if we think about this wheel right here, and we've got some point P, and we know our center, Well, then the distance from the center out to P is the radius, and in this case, it's A. And that's, how did I know that? Well, I didn't know that. They were nice enough to label it in the diagram for me. Okay? So they gave you A in the diagram, so take it and run with it. So we can say the radius of the wheel is A. So when the wheel has turned t radians, the base of the wheel is going to be a certain distance from the origin, right? Here's the origin, and then here will be the base of the wheel. And so the base of the wheel, or the wheel's center, is going to be at this point right here, AT comma A, right? So this distance AT, that's the distance from the origin to the center, and then A, well, A is just the radius of your circle, so that's your height up. So then this is AT comma A. Okay? So we can say the wheel's center is at the point AT comma A when the wheel has turned t radians. Okay? And so the coordinates of P the coordinates of our center are going to be, so we need a value for x and we need a value for y. Now, so the coordinates of point P, well, if you think about the horizontal distance is AT away from the origin, but it would be nice if we had some kind of formula that we could use to find our distance from the origin no matter what. So what if we had only turned so many radians and we were right here? What would our distance from the origin there be? And so it's going to be AT plus A cosine theta. And so theta is this theta right here, and that's the degrees that we've turned, or the radians that we've turned. So where we're getting this cosine is from our right triangle. Okay, if we set up a right triangle right here, and then we can use this to find our relationships, then we can get AT plus A cosine theta as our equation for x. So then in that case, if that's x, then y is going to be A plus A sine theta. Okay? So now ultimately what we want to do, they're asking us to find parametric equations. So we want to find some equations where at the end the only variable that we have in our equations on one side of the equal sign is going to be our parameter. And in this case we can use t. So what we want to do is we want to express theta in terms of t. So we only have t as our parameter. Right? So we want to end up having only t at the end. Now, so t is going to be the amount of radians that we turn, and then theta, theta is that angle that we can form with our right triangle that goes up to the outer edge of our circle. So what we can do is we could say that t plus theta is going to be 3 pi over 2. So then theta is 3 pi over 2 minus t. So then we can write some trig identities, okay? And so we know that, let's see, the cosine of theta, well, the cosine of theta, well, if theta is 3 pi over 2 minus t, that's just going to be the cosine of 3 pi over 2 minus t. And then we could say that sine of theta is going to be the sine of 3 pi over 2 minus t. And then what we could do here, well, if you remember your co-function identities, so I'll just do a quick refresher to that. Let's see, I'll do this down here. So, for your co-function identities, that would be sine pi over 2 minus x is equal to the cosine of x. And then we could say that the cosine of pi over 2 minus x is equal to the sine of x. Alright, so if we have the sine of 3 pi over 2, well, that's the same thing you know from your trig as negative sine of pi over 2. Alright, so if we go back up here then, so if we use these identities and go back up here and rewrite these, so cosine of 3 pi over 2 minus t, right, and then this should be a minus sign right here. That's going to be, we can say the cosine of 3 pi over 2 minus t is going to equal negative sine t. And then for this problem, we could say that the sine of 3 pi over 2 minus t is going to equal the negative cosine of t. Okay? So, now we started off with x is at plus a cosine theta, and we got the at from the distance, the horizontal distance that we're going to move. So now we know what cosine theta is in terms of t. So cosine theta is going to end up being well, that'll be negative sine t, and then sine of theta will be negative cosine t. So then if we take this bit down here and use this relationship, this co-function identity that we just talked about, we can say x is at minus a sine t, and y is a minus a cosine t. And those are your answers to example 1. Okay, so just working through some of those problems and knowing what they're asking for and making the substitutions. You won't ever have a problem like this on the exam. Cycloids don't usually come up on the exam, but it's good to kind of know how to work with these, and then it also kind of gives you a good way to work with parametrics. It gives you good practice with that. Alright. So, the next thing that we can do we can do example 2 to figure out the arc length of something. Alright, so what we want to do is find the length of one arch or one curve over one period of the cycloid given by x is 3t minus 2 sine t and y is 3 minus 2 cosine t. Alright, so if you go ahead and graph that, let's see. If you go ahead and graph those parametric curves, your arch is going to look something like that. Okay, so everything's defined, and that goes through one whole rotation, and we're not repeating anything. So then we can start off by taking our derivatives of our x and y functions with respect to t. So we can say dx dt is 3 minus 2 cosine t, and dy dt is going to be 2 sine t. So then we can say that dx dt squared is going to be 9 minus 12 cosine t plus plus 4 cosine squared t. So then our dy dt, the whole thing squared, is going to be 4 sine squared t. Okay, so if we use our let's see, if we use our formula to find arc length or distance along a curve, so we'll have the integral going from 0 to 2 pi, right? And then on the inside, well, we have this giant polynomial with trig functions. We're going to have 9 minus, actually I'll go and do this off to the other side. We'll have 9 minus 12 cosine t plus 4 cosine squared t. And if we're adding our dy dt to this and putting this all under 1, well, dy dt, remember, is just 4 sine squared t. Now, if we look at this, the 4 cosine squared t and the 4 sine squared t, well, in this case, if we factor out the 4, we'll get cosine squared plus sine squared, which is 1. So, it looks like this. Right? And then you can do 1 times 4, which is 4. So we have 9 minus 12 cosine t plus 4. Okay? And then, well, 9 plus 4 is just 13. So we have 13 minus 12 cosine t. And so now what we can do is we can take the integral of that. So I'm going from 0 to 2 pi, and I can do my integral of 13 minus 12 cosine t dt. Okay, and so this is something that we would want to mint. It's a little tricky to figure out on its own, and so if we go ahead and mint that, we're going to get 21.010. Okay, and so that would be the length along your curve.